morning. Hi. Good to see you all here.
Morning.
Hi, Sean and Ben and Mark and Fort and Jack and Brandon, Evan and Sanjot. Good morning.
Morning.
Good morning, Professor.
Hi. Did you have a good day yesterday? We've got a holiday coming up.
When you say we've got a holiday coming up, are you referring to Thanksgiving?
No, I'm referring to tomorrow.
Why is tomorrow a holiday?
It's Veterans Day.
Oh, okay.
So if you have any on-ground classes, campus is going to be closed. Oh, well, I think actually today is going to end up being kind of a short day. We only have one graph algorithm to cover, and then that's it. And there's no homework for this week. So you get a little break from that as well.
Appreciate that.
Oh, so do I. All right. Well, so today we are talking about the shortest path algorithm. And, actually most of you probably use this nearly every day. Put your mapping application on your phone. You want to get from point A to point B, or where you are now to some other place. You type in the destination, and then the mapping service, whether that's Google Maps or MapQuest or Apple Maps, is able to find that shortest path, in just like a second or two, maybe even faster than that. So it's pretty quick to do that. And you have to consider that the graph that these companies are using is huge, right? It's basically the entire planet with all the roads and intersections. And the graphing algorithms or the mapping algorithms are pretty sophisticated these days. They're not just finding the shortest path in terms of distance. They might be finding the shortest path in terms of time. Or I think Google, I just saw a headline saying is testing out a map that shows you the one that uses or has the least ecological impact.
Yeah, my phone has it.
I think that means like uses the least gas or something like that. Or is that what it is primarily? Uses the least gas?
Yeah.
Yeah. So I don't know what all is involved in that, but it's probably things like minimizing the number of starts and stops you have to do, and finding the roads where the speed is the most constant, because that uses less gas when you're doing that. So that's kind of neat, which means that their graphs aren't just simply intersections with roads connecting them and a weight that indicates maybe the distance. Those weights indicate other things like time or speed or, in this case, the amount of gas being used to go from this intersection to this intersection. So we're taking a look at this shortest path algorithm. Now this one you can see is a little more complex than Prim's minimal spanning tree, but we'll work through it. I've got two examples to work through, and then I'll show you, other than maps, I'll show you another different practical application for the shortest path algorithm. So let's say I want to go from A to E. Now this is a pretty small graph, and so you might be able to figure out what the path is. But if you're doing this kind of like by visually inspecting the graph, you might end up doing more or less trial and error. Kind of like going, well, is this the shortest one? No, maybe I can do it like this. No, maybe I can find some other path. And so you just kind of do trial and error. But the computer doesn't do so well with trial and error. It actually has an algorithm to follow. So here's how you do it. So we're going to go from A to E. So A is going to be our start, and E is going to be our destination. Let's mark that here. Let's go start and end. And so the way this algorithm works is, in addition to finding the shortest path from our start to our end, it also, along the way, finds the shortest path to every other vertex in the graph. So what we're going to do is we're going to label each one of the vertices with the amount of weight, or the amount of time, or the amount of distance it took to get to that vertex from the start. Now, last time I said that this algorithm is kind of like, I visualize it as kind of like dropping a pebble into a pond and watching the ripples go out. So we're going to drop the pebble here at the start, and then these ripples are going to start flowing through the graph. So they're going to go this way, and then the ripples are going to go this way, and then they're kind of going to go this way, and they're going to eventually find their way to the ending vertex. But along the way, they've traversed all the other vertices, and so they end up calculating the fastest way to get to all the other vertices as well. So we're going to label each one of the vertices with how much information we have so far about the fastest way to get to that vertex. And we'll label A here with 0, and the others with infinity. And the reason why we're doing infinity is that's just kind of a placeholder that means we don't know yet how long it's going to take to each one of those vertices. So we'll just set it to the maximum value we've got, which is infinity. So that's step 1 here. Assign every vertex a tentative distance, set it to 0 for our initial vertex, and infinity for all the other vertices. So that's what we did here. Okay, next step. Set the initial vertex as current. So I'm going to label the current one by drawing an arrow to it. That's our current vertex. So imagine we're kind of like an explorer. This is where we are right now, and we're going to start exploring the edges of the graph. Create a set of the unvisited vertices called the unvisited set. So those are going to be all these other ones here. Consisting of all the vertices except the initial one. So along the way, what I'm going to do is I'm going to check off the vertices when we have completed them. So if they're visited, considered to be visited, I'm going to check them off to mean that they're done. Okay, so for the current vertex, consider all of the unvisited neighbors and calculate their tentative distances. Okay, so we're going to start here at A, and we're going to look at all the unvisited neighbors, which are D and C, and calculate their tentative distances. Right now, their tentative distances are infinity. We're going to replace those infinities with some actual numbers. So if we start at A and travel along this edge, we know now that it takes 9 to get to C. So we're going to replace the infinity with 9. And then we're going to start at A again and travel along this edge and discover that it takes 4 to get to D. So we'll update this infinity with 4. Okay, see what we did there? We started at our current vertex. We traveled along the 2 edges coming out of it, and then we updated the tentative distance to each one of those neighboring vertices with a new number. Okay, so that's step 3. So it says, even though a neighbor has been examined, it is not marked as visited at this time and still remains in the unvisited set. So we're not going to check off these ones here yet just because we got to them. The reason for that is there might be better ways to get to these vertices rather than what we just discovered. So, number 4. When we are done considering all the neighbors of the current vertex, mark the current vertex as visited and remove it from the set. So we are now going to check this one off. It's done. We will never have to go back to it again. A visited vertex will never be checked again. This distance is recorded now as final and minimal. Okay, step 5, if the destination vertex has been marked as visited, which it's not, then we're done. But we haven't done that. So now we're going to set the unvisited vertex marked with the smallest tentative distance as the next current one. So we look at all these numbers, 4, 9, infinity, and infinity, and we pick the smallest one. That's going to be 4 right here. So this is our new current vertex. Phew. All right. Let's repeat the process over again. So go back to step 3. For the current vertex, consider all the unvisited neighbors. All right, this one's already visited, so we don't have to look at it. The only unvisited neighbor we have is C. So let's travel along this edge going towards C. And what we're going to do is we're going to take this tentative distance of 4, add it to this one, and come up with 7. Right? I did 4 plus 3 is equal to 7. All right, so we do 7, and that's better than the 9 we had. So we found a new distance that's better than what we calculated before. We can now update this one to be 7. Oh, you know what we should do? Along the way, we should be keeping track of where we came from. I keep forgetting to do this. Every time I do this algorithm, I forget to do this. So in addition to putting a 4 here, I'm also going to put A to indicate that I came from A. And this 9 had an A, but this 7 has a D because I came from D. I'm going to need that in order to be able to backtrack through the graph later on to find the path, the shortest path. Okay? All right, so now this one is done because I looked at all of its unvisited neighbors. All right, so 7, infinity, infinity. Pick the smallest one. That would be the 7. So this is our new current vertex. We're going to look at all of the unvisited neighbors. We're going to take the 7, add it to the 4, and come up with 11. That's better than an infinity. So we'll replace the infinity with 11, C. And then we'll do 7 plus 9 is 16. That's better than infinity, so we'll update it with 16C. And now C is done. Repeat again. Pick the smallest one. That's 11. So this is our new current vertex. Not going to go this way, right? That heads towards C, which is already done. So we're going to go this way. We're going to do 11 plus 4, which gives us 15. 15 is better than 16. So we'll update the 16 with 15B. And now this one is done. B is done. And then finally, we'll do E here. There's no unvisited ways to go, so this one is now done as well. So now that we've reached our destination and we marked it as done, we are finished. And so we can see the path here. If we backtrack, starting at the end, we go back to B, and then from B we go back to C. From C we go to D, and from D we go to A. So our path going backwards is E to B to C to D to A. And then we can label in the weights 4, 3, 4, 4, for a total of, what's this, 15. So the shortest path to get from A to E is to go to D, C, B, and then E. So interestingly, it is not necessarily the one with the fewest edges. Okay, I know that was complicated, but let's do it again with a different graph. So I want to go from A to H. So here's my start. Here's my end. All right, there's a lot of edges, a lot of vertices, but we'll work through this. And if you kind of miss a step or you get lost, then you can watch the video later and you can back up again. Back up and watch it. Okay, so this is our current vertex. Oh, we're going to start by labeling A with 0 and all the others with infinity. All right, let's start. So we're going to look at all the unvisited vertexes from our current one. So we're going to go this way and this way. We're going to take 0 plus 6, and we're going to come up with 6, and that's better than the infinity. So we'll update this with 6a. And this one here gets updated with 2a. And then this one is done. In fact, maybe instead of checking it off, I'm just gonna cross it out. All right, so let me ask you, which vertex becomes our new current one?
E.
E, because it's got 2. I'm not going to go back towards A, because that one's already done. I'm going to look at F and I. So what do I update this infinity on F with? 5. Good. How do I get the 5? It's 3 plus 2. And what do I update the infinity on I with?
5e,
No?
7e.
7. Good. 5 plus 2. And now E is done. All right, which one is next? Which one will be
F.
our new current one? F. Why? Because it has the lowest weight. All right, so we'll go this way. We got 5 plus 8 is 13. That is not better than the 6. So we'll leave the 6. Then we'll go this way towards G. We got 5 plus 4. That becomes 9F. And then we'll go this way. And we've got 5 plus 7. And that's 12F. And now this one is done. Which is our new current one?
It's going to be B.
B, right? Because it has 6. This one has 9, this one has 12, this one has 7, and the others are infinity. Okay, so we're going to go this way towards C. And we're going to update this infinity with what?
12B.
12. Good. 12B. And we get the 12 by adding the 6 and the 6 together. And is B now done? It is done because we can't go that way, can't go that way, and we already did this one. So B is now done. Which is our new current one?
C.
No? I, because it has 7. 7's the lowest number. All right, so can't go that way. So we're going to go towards J. Do we update the number on J?
Yes, with 10.
With 10. 7 plus 3 is lower than 12. So we'll update this with 10I. And now I is done. Which one is our next current one?
Should we mark J as done as well?
Nope.
Okay.
We got
will
G.
eventually, but not yet. G is our next one, because that's the lowest number. Okay, so we go this way. Do we update the number on C? Yes, we do. With what?
11.
11. 11G, because it's better than 12. Let's go this way. What do we update this infinity with?
15G.
15G. And then we'll go towards K. And we'll update this with 15G as well. And now G is done. Okay, which is our new current one?
Now we go back to J.
Now we'll go back to J because it has 10. And then we'll see that we can't go this way because we're going towards F, which is already done. And we can't go this way because we're going towards I, which is already done. So we will now mark this one as done. All right, we got 11, 15, 15, and a couple of infinities. So C is our new current one. All right, we'll go this way. What do we update this infinity with?
16.
16, you're getting it, yeah. 16C. And is C now done?
Yes.
Yes, because we can't go this way, and that one's finished. Okay, which one's our new current one? Now we got.
Do we just pick arbitrarily?
Now we just pick arbitrarily.
This is where I got
right?
stuck, yeah.
Yeah, just pick arbitrarily. Now, if you're a computer, you'd probably just pick the one that comes alphabetically first. So maybe we'll pick this one. Okay, so we'll go this way. And we got 15 plus 3, which is 18. 18 is not better than the 16, so we'll leave it. Then we'll go this way. And we got 15 plus 5, which is 20. And now this one is done. Now, according to our algorithm, if we flip back over here, it says if the destination vertex has been marked as visited, or if the smallest standard distance among vertices to the unvisited set is infinity, then stop. The algorithm has finished. So at this point, we're done. Now, if we had broken that tie and we had gone with k instead, we would have calculated this one here to be 17. And then we would have calculated this one here to be, well, this one would have been 17. And then this one would have been 15, right? We saw this one as 15. So we would have then made h be the current one. And then our algorithm would have stopped one step later. So eventually, we would have stopped, even though we haven't marked all the others as being done. The fact that we've marked this one as being done means we're now finished. All right, so let's backtrack. Let's go H. That goes back to G. G goes back to F. F, got to find F on there. That goes back to E. And then E goes back to A. So our path through here is A to E to F to G to H. That's the shortest path. So the total is, of course, 15.
Can you explain again why we stopped where we did?
On H?
Yes.
Well, as soon as we mark this one as visited, then we're done.
Okay.
Also, we had picked H as being our destination, so we stopped there.
I see. Okay.
I mean, we could do it again if we pick, like, let's say, L as being our destination. And then, you know, I think I designed this graph here. So if you pick, like, L, then you end up, like, you know, kind of zigzagging your way through this graph. So that's the shortest path algorithm. So a little more complicated than Prim's, but this is basically the algorithm that Google Maps and Apple Maps and MapQuest use millions of times a day to find the path between 2 points on a graph. So here's a practical use of the shortest path algorithm. And so you've got this photograph here. And what you want to do is you want to shrink it down so that it's less, so it's narrower. So here's our original image right here. Actually, let me go back here to the Wikipedia article. All right, so you want to take this image here and you want to make it narrower. There's a couple of ways to do it. One is you could just simply resize the image. You could just go into your photo editing application and you can just say, make the width narrower. And what it will do is it will just squeeze the image, but this is kind of undesirable because everything now appears to be tall and skinny. You know, alternatively, you could just crop the image, but this is also undesirable because it crops out parts that might be important. So this algorithm called seam carving is actually fairly new. It was invented in 2005, so just 16 years ago, and it won an award in 2015. And seam carving is a way to resize an image without cutting out the important parts. And it's really cool. So the way it works is you start with an image, and then for every pixel in the image, you look at the color of its neighbors, the colors of its neighbors. And from that information, you can calculate what the algorithm calls the energy of a pixel. It's basically a calculation of how different the color of this pixel is from its neighbors. So if the neighbors of a pixel are similar in color, it has a low energy. And if they're more different in color, it has a higher energy. The idea being that areas like the sky here have low energy, and areas where there's lots of detailed information have high energy. And the idea there is that high energy parts of the image you should leave, and low energy parts of the image you can get rid of without affecting the image too much. So here's what the image looks like after all those energies have been calculated. You can see that the areas of the sky where the color is mostly the same have low energy, or is a kind of a dark color here. And the areas where there's lots of detail, lots of changing colors, you can see are represented using a lighter color, so they have higher energy. So as you may know, an image is basically just a matrix of pixels, and that's what I've kind of represented here. And then you connect up all those pixels in a graph. This is what the graph looks like. You've got one extra vertex at the top and one extra vertex at the bottom. Those aren't really part of the image, but they're part of the algorithm. And then you connect up the pixels in this graph that basically just connects up the neighbors. So all the edges are like pointing downward. They're actually directed, but I didn't have time to draw all the arrows in. Right? And then you find a path through the pixels from the top to the bottom with the lowest overall energy. So you start up here and you find a path through the image that has the lowest overall energy. And what's going to happen is, because this is a directed graph that's pointing downward, you're going to select exactly one pixel from each row of the image. And those pixels are also going to be neighbors of each other, so it's going to look kind of like a lightning bolt as it goes through the image. Right, do you see that? So as you come up with a graph through the image, you're always going to pick exactly one pixel out of each row. And so you remove those. And then that squishes the image inward by one pixel. And then you just repeat the process over and over again. You calculate the energy of all the pixels. You find the shortest path through the pixels with the lowest energy. You remove those pixels and you squish the image in by one pixel. So every time you run this algorithm, you squish the image by one pixel. You make it one pixel narrower. So here is an illustration of all the different paths that it found through the image with the lowest energies. And then this is the resulting image. So the castle has been, let me scroll back over here. Here's the image of all the different paths through the image. Here's the resulting energies, and then here's the resulting image. So you can see that the person and the castle have been brought closer together, but the castle has been retained and the person has been retained, and everything else has been eliminated. So here's a demo of it. You can start with an image. And then it finds a path through the image. And we'll do this little demonstration. Let's see, where is it going to do it? I think it's going to do it right here. So let me zoom in. Oh, nope, stop. I can see it's actually doing it in several places. So let me scroll this. Here we go. You can see the castle is just sliding closer and closer together. Now, eventually, they're going to get so close and all the low energy pixels have been eliminated. It's going to start eliminating other stuff. So at some point, it's going to start wildly distorting the image. That's crazy. Sean, you said you're playing with it in Photoshop right now, and it's pretty cool, huh?
Yeah, with the same picture that they're using here. It's neat.
And we can actually upload our own image. Let's see. I think I've got some pictures here. That one's not so good. How about... Let me try this one. I don't think it'll do very well with this one either because there's lots of detail in this whole thing. But let's see what happens. Yeah, it's just gonna squish the scuba diver. Poor guy, he's getting squished. And so the problem here is that since there's so much going on in the image, that it just basically has to compress the whole thing. So that one's not very good. Let's. Do I have anything else here that's good? Oh, here, this one. This one's actually pretty good. Not bad. So I kind of had 2 points by showing you that. One is this is an application for the shortest path algorithm. And the other is to impress upon you that not everything has been invented. I've run across people who say, like, everything that has possibly been invented has already been invented, so there's nothing else to do. But this algorithm is pretty new, right? It was only incorporated into Photoshop in the last decade or so. And you might think, well, now everything has been invented. That was the last thing that ever had to be invented. That was it. We're done now. From now on, everything else is just boring. But no, there's new stuff to be done all the time. I saw a demonstration. Actually, every year, Adobe puts on a conference where they kind of show off some of the latest things they've been working on, not yet incorporated into their products, but just kind of like as a little preview. This is what their engineers have been working on, kind of in their spare time, and we're considering these things for inclusion in our products. And I saw this demonstration where the engineers basically took the problem with taking pictures, right? You hold up your camera, you take a picture, but if the light is kind of low, or if you can't hold the image really steady, then there's going to be like a little bit of a blur, right? Not caused by the image being out of focus, but caused by the camera moving. Now these days, in the really modern like cell phones, they actually get around the problem somewhat by using the motion sensor inside of the phone to detect when you are holding the phone the stillest, and then they take the picture at that moment. So they use the motion detector to determine when you've stopped moving the camera, and then they take the picture right then. So you get a nice sharp image. But before we incorporated those anti-shake kind of mechanisms in there, you often had a problem where the image had a little bit of a blur due to the camera moving a little bit. And so what these engineers showed, and actually photographers have always considered like camera shake blur was just totally impossible to deal with, right? You just had to basically make hold the camera less still or more still, or you had to use a faster shutter speed in order to stop the action. But what these engineers showed was that they could actually remove the blur due to the camera shake. And so they took an image and they put it up on the screen, And then they ran this filter on it, and boom, it came out sharp. And everyone's jaws just dropped in the room. It's like this was a problem that photographers have had for decades. And these engineers basically solved it right there. And by just analyzing the photograph, was able to figure out how each one of the pixels was smeared, because they're all basically being smeared in the same direction because of the camera shake. And they were basically able to unsmear the photo and sharpen it up. And that was just like a few years ago. I mean, all this stuff is new in being able to do photo manipulation. There's another thing that they were working on maybe 10 or 15 years ago, which was, if you remember, there was this thing called the megapixel race in digital cameras. The first digital cameras that came out had really small sensors, a relatively small number of pixels. And then there was this race that's still continuing somewhat to increase the number of pixels on the sensor frame. And so you came out with cameras that had like 1 megapixel and then 4 megapixels, which is mega means million, and then 8 and then 14. And now I think they're like up to like 30 or 40 megapixels on this camera frame, which means your images, of course, your image files are huge, right? Because there's just almost billions of pixels to deal with. But the problem is, as you make as you increase the number of pixels, the pixels get smaller and smaller and smaller, and then due to physics, the amount of what's called noise in the image has to increase. When you have larger pixels, they're able to kind of even out the colors more, but as you get the smaller and smaller, the contrast on each pixel increases to the point where there's kind of like all these little speckles all over the image. They can counteract that somewhat by using post-processing in the camera to analyze all those pixels and then kind of smooth them out. So even though you might have 30 megapixels, because of the smoothing, you effectively only have maybe 10 or 5 megapixels in the camera because of the smoothing. You can still advertise yourself as being like a 30 megapixel camera, but because of the smoothing, you're basically averaging out all the pixels, and then you get effectively fewer pixels, but that's beside the point. So during this megapixel race, there was this idea like, what if we could actually go the opposite direction? What if we can make a camera that has 1 pixel? Just one. It just measures the amount of light coming on it. That's it. How could you possibly even take a picture with that? I mean, if you had just one giant pixel, one giant sensor that measured one amount of light, and you have a lens in front of it, and the lens is projecting an image onto that pixel, how could you possibly form an image out of that? Because all it would see is just kind of like an average of all the light. Well, so these engineers had this idea that we would put normally there's a shutter in front of the image, in front of the sensor that blocks the light when you're not taking a picture, then unblocks the light when you are taking a picture. But inside of that shutter, there would be a series of LCD pixels on there that they could turn on and off, basically making a checkerboard pattern that they could individually turn them on and off. And so the idea was you have 1 pixel, and then in front of it you have this shutter that has a grid on it, and you can turn on and off the individual cells of the grid, which would let light through in that cell or not let light through. So basically, imagine you've got your sensor, you've got this grid, and you've got this image being projected through it. So if you turn on and off those pixels, you let different portions of the image through to the sensor, and therefore it gets different amounts of light. So the idea was, take a series of images, but change the cells that are on or off, and that changes the amount of light falling on the sensor. And then with a huge amount of processing on the back end, you can reconstruct what the image looks like based upon just the light falling through that grid of pixels. And so I thought, I mean, it never went anywhere, but it's kind of like taking the whole problem and just flipping it entirely upside down and saying, instead of doing more pixels, why don't we do less pixels?
From what I understand, there was also a camera developed about a decade ago. I don't know if it's applied at all yet, but it somehow captures like the quantum state of the light itself. It's not taking a 2D image, it's taking like a photograph of the light in a chamber.
Mm-hmm.
And then it can use that with the computer program to recreate the image with like any depth of field or focus or anything. It's got all of the light contained in this like file, and then it can build the image out of that in any of a variety of ways, you know,
Yeah.
with various depths of field or zoom or
Yeah, that
whatever.
was called the Litro camera. And
Whatever happened with that? I haven't heard
well,
anything. Are they using it in physics yet or anything?
no, I don't think it really went anywhere. Um, you know, I never really looked into how that camera worked, but I spent a lot of time like speculating because it was a patented process. So no one was, or it was not a patented. It was a, you know, a secret process. So no one really knew how it worked. But what I imagine happened was you've got your light sensor here, and you've got this lens over here, and I think, and because the camera was like this, it was long. It was like a 3 or 4 inch long camera.
Yeah, it's like capturing the light
I
in the chamber and the lens,
I
kind of.
think though probably the way it worked was they just racked the focus in and out on that lens so that it would take the image with different focus points. So you'd get maybe 20 or 30 images internally at different focus points, and then you could just, using your post-processing software, pick which image or images you wanted to use as your focus point for your photograph. So if you wanted to select your focus as being on the subject, which is up close, you would pick that image. But if you wanted your background to be blurred, you would use a different image that had the background, the blurred image. Or if you wanted both your subject and the background to be sharp, you would pick the image that has the sharp subject and the image that has the sharp background, and then merge them together. That's my guessing. That's probably how it worked. Right?
That would work.
I don't know if they really were able to create like a brand new type of sensor that would capture quantum information. That might have been marketing speak for, we just took a bunch of images in a row and then basically stack them on top of each other, and then you just pick which focus you want out of out of the result. I think that's kind of like the way the multi-lens systems on the new phones work. Is there's one lens up here, or they have two different lenses. When you go into portrait mode, it uses one lens to focus on the subject, and it uses the other lens to defocus the background. And then they just merge those two photographs together. That's how I think that works. What other? Oh, and then there's a pretty good video by, I think, Tom Scott, that talks about how things like, you know, when you're doing videos and you eliminate the camera shake, right? That technology has moved forward over the years to where now they're pretty sophisticated. Let me see if I can find that video. What is that called? Motion? No. Camera. Oh, video stabilization. That's what I'm looking for. Let me see, how long is this video? It's only a few minutes long. Let me see if I can bring that up. I gotta change some things here. There we go. This is the one I want to do here. Let's see if we can get the audio from this. No? Is it this one? Yeah. I'm trying to get the audio to work. Hold on, this is not something I normally do. So, why isn't the audio working? Let me see. I think I don't correctly have the audio feeding back into the system. That's the problem. Oh, let me try it over here. Let's see if it'll work over here.
Out of curiosity, I just looked up the megapixels on the James Webb telescope. If anybody wants to know, it's a 937 megapixel camera.
And you know, the Hubble telescope, it's not that much. I mean, that telescope was made, what, 30 years ago? So the size of its sensor, even though the sensor itself is probably fairly big, the number of pixels is pretty small.
Is James Webb optical?
Yeah. Except that it's most sensitive not in the visual range, but more like in the infrareds and ultraviolets.
It's got special sensors in it that can change the sensitivity based off of electrical impulses. So there's like ions in the pixels that can be like charged or whatever to make it more sensitive to different wavelengths.
Let's see if this works. Any audio? No. Oh, let's try this. No. I got to work on this problem here, getting audio out of my computer and into back into the system.
Is there not like a with audio tick in the share screen in Zoom?
No, it's the way I'm running audio through all of my equipment. Oh, let me see. Maybe it's over here. No.
Is starting to move, then you might have a bit of a problem because you have nothing in the background to lock onto for the entire shot.
Back this up now.
You'll have seen the videos on YouTube with stabilization, that kind of gliding through the matrix effect that takes out camera shake. But how's it work? Well, to explain that, we need to go back a little bit to how it used to work, the naive approach to doing camera stabilization. See, the early way to do it, you know, back when computers had a reasonable amount of processing power, was to pick some object somewhere in the background that was fairly bright, lock onto it, and then just keep that in exactly the same place, no matter how much the camera moved. Give us a bit of shake, Matt. There we go. Then, if you want to add a bit of rotation and scaling to that, you lock onto a second thing on the other side of the frame, track both of them, draw a line, and keep that line rock steady as things rotate. There we go. And that's okay if your shot is static, but if your shot is starting to move, then you might have a bit of a problem because you have nothing in the background to lock onto for the entire shot. You have me, but if you lock onto my face, it starts to look very weird indeed. And then you start using a new approach, one that you'll find in iMovie and in older versions of Premiere and things like that, which is you look at the entire frame. You work out where everything is going, every pixel, what has changed from one frame to the next, and then you assume the big movement, the big background movement in there, that is how the camera has jogged. And you try and reduce that over time. You zoom in a bit, you crop a bit, you rotate a bit, and you try to minimize that. Which works okay with old school cameras, but nowadays, modern cameras like this have something called a rolling shutter. Which means, oh, this thing's heavy. Which means that the top of the frame is a fraction, a hundredth of a second ahead of the bottom of the frame. And that screws up all kinds of computer vision algorithms. So you need to deal with that. And nowadays, the modern version, the latest version of CS6 and iMovie and things like that, use what Adobe call subspace warp. The ability to stretch and twist different types of the frame, different parts of the frame in different ways as it goes on. Kind of merging and melding the whole thing, that's what causes that kind of gliding odd effect. Because if I put out my hand towards you and you move the camera up and down slightly, different parts of me are visible from behind there. Ultimately, you can't know what the pixels should have been. Okay, we're still one away, because YouTube has a bit of a strange effect. They have that kind of timing thing. That's down to a paper that they released and put online. It's one of the computer vision conferences trying to work out how to do cinematic stabilization. So what they do, hold the camera steady, Matt, whereas old stabilization would have just, tried to ease that, tried to make that as simple as possible. Nowadays, it tries to turn it into a camera move. YouTube will start a camera shot and stop it. Start a camera shot and stop it. And they will try and work out a 3D solution for everything that's going on. That's the most modern technology they've got. But give it a few years, there might be something better. Because right now, what you have are films where old 2D movies have been updated to 3D, which means that they are essentially extrapolating where a camera would have been. If you could apply that to stabilization, if you could work out what would happen if I kept my hand there and the camera happened to be where it should have been, well, then you have a much better stabilization technology. Then you have something that could produce steady cam shots out of nowhere. We're not there yet. Light field cameras, they're coming in, might be able to help with that. But in the meantime, well, YouTube stabilization is the best we've got. That is more or less mathematically how it works, and that is something you might not have known. There's a big sign over there.
That's pretty cool, I thought. How stabilization technologies have improved over time. And so, the idea behind that YouTube stabilization is they work out like, the camera's over here, and then it's over here, and then they figure out what the image would have looked like if you had smoothly panned the camera from that point to that point. Adobe is also working on not only video, but they're working on audio as well. Like how can you, and so they had, a few years ago, they had this demonstration of being able to analyze like an actor's voice. So they would, this thing would listen to an actor saying a whole bunch of lines through a movie, and then by pulling out the different sounds the actor make, they could basically reconstruct or construct brand new lines for the actor to say that the actor had never said. And the idea there is that for people doing things like podcasts and movie production or audio production, if let's say you had hired the actor for a day and you need them to say a line that they didn't have time to do or you forgot to do that day, you could then go and have them electronically say that line and then not have to bring the actor back in to record that line. So, ostensibly it was going to be a huge time saver and money saver. But then people quickly figured out that with this technology, you could basically have anyone say anything. And you can imagine where, people could take this very quickly. They could basically claim that maybe, let's say you committed a crime or something like that, and so you wanted a friend to basically give you an alibi. Well, you could just electronically construct that alibi, right? You could have that friend say that you were somewhere where you weren't, and it would be like no one could tell in court that this had happened. So Adobe demonstrated the software, and then there was a huge outcry to say, like, well, basically now, we can't trust any recordings of anyone because they can all be faked. And so it never kind of saw the light of day. That product never did. So there's definitely like limits to what we can do with this technology. But the fact that people now know that it's possible means that other people besides Adobe are working on ways to do this. I mean, you've heard about video and photographic deep fakes to construct an image that never existed. Well, now you can do it with audio as well. So imagine you could construct an entire movie with images that never existed, with audio that never existed. Is that worthwhile, or is that kind of scary?
I heard maybe like a year ago that somebody was working on a computer program that you could just you could take an audio recording in a room.
Mm-hmm.
And so like the vibrations from a conversation that happened a week ago in the room are just very, very faint. They're still there. It's just fading out. It's very faint. And so the idea was to take an audio recording in like a quote unquote silent room, and then remove all of all of these known patterns that you have some recording of what had happened in the room, and remove all of that. And then you could like isolate and amplify sounds that had happened before, things that were no longer audible, but were still, resonating in the room slightly by, reconstructing it by taking a bunch of pieces out and then reconstructing it.
That sounds a little freaky for something that happened long after it happened, but it's not that far-fetched, maybe for something that happened a few seconds ago, to have things in the room still vibrating a little bit. I do know
that was like what they had empirically done, and they had recordings of those full seconds to be able to remove whatever they wanted to. The goal for it was like a physics team at MIT or something. The goal for it was to be able to do something similar with electromagnetic vibrations in cosmology, and be able to extrapolate things that happened in the past by removing the noise on longer scales. That was like what they were after.
Yeah. They actually, along that lines, I just saw or heard on a podcast maybe, where they've known for a long time that you could record a conversation happening in a room if you aimed a laser at a reflective surface, like a window from outside. And because the window is vibrating very gently to the conversation happening in the room, the laser being pointed at it is reflecting slightly differently. And then you can measure the reflection coming off of that and basically figure out what's going on inside the room. So
you can actually do it from a video of a light bulb in the room. If you can see a light bulb in the room, you can do it from a video of that light bulb.
That was the one I think I just read, where they had a speaker in the room, just a standard PC speaker, which has an LED on it to say when it's on. But because the speaker is drawing power from the computer, and the LED light is also drawing power from the computer, the LED light will flicker very slightly based upon how much power the speaker is drawing. And so if you can measure the light output from that LED, you can then from that deduce what the speakers are doing, and then get a fairly good recording of what the speakers are playing. And so I think this is what you heard is that LED that's in the speaker, because its brightness is affected by the current being drawn by the speaker itself. You can measure what the speaker is doing. You do need line of sight to that LED, and they said, like you said, even a video recording of that LED would work fairly well, although I think it was a little muffled because you don't get some of the high frequencies. But that is kind of, scientifically it's interesting, right? But it kind of speaks to a lot of things about what you thought was private conversations may not be private conversations. I see Sean there, he's wearing headphones, and if those headphones have a power light on them, then if they don't, but some do, right? Some of them have, if you have a light that indicates that Bluetooth is on, you could then measure the amount of light coming off that LED and be able to listen to what you're listening to. So what you think is a private conversation in your headphones could actually be listened to by someone who could see that light.
One of the things, back to the vibrating windows thing, I know that a lot of government buildings and especially embassies, they have little vibrators on the glass to, thwart anyone trying to pull information from the glass through, a laser. But
basically introducing
noise,
fake noise.
Yeah. But the video of a light bulb thing, that really kind of throws that out the window. That's a good defense.
So they said,
I mean, you would need a really high fidelity video of the light bulb. You'd kind of need the camera in a fixed position right next to the light bulb to be able to actually see the light bulb vibrating enough to I mean, maybe not. Maybe if you had a really nice camera and you were looking through the window.
It's a good thing they don't make vibrating. Good thing they don't make nice cameras and nice lenses.
Well, they said it was easy to thwart that. Just put a piece of tape over the light. I mean, we've gotten off topic here, but the bigger picture is not everything has been invented, and there's still stuff out there to be invented. And there's still stuff out there to be discovered. So we can find tons of examples of these sorts of things, of finding different channels of communication that people didn't normally think about. It wasn't that long ago that malware writers were figuring out how to get computers to send malware to other computers in the room, even if there was no network connection between them. And they got the malware to basically click the speaker on one computer, and the other computer would have its microphone on and would hear those clicks. And those would basically be a way to send ones and zeros across the computers. And you could do the clicks so slow that no human would ever hear them. Like you do one click like every 2 or 3 seconds. And it doesn't have to be a very audible click to humans. It can just be a almost inaudible one, but the computer can still pick it up. And then over time, eventually they can send information to the other computers. So even though there's what's called an air gap between the computers, which means there's no direct network connection between them, they can use literally the air to send information from one computer to another computer. And that's almost undetectable, right? Because the clicks are only coming once every few seconds, and then humans can't hear them. And so who would know? Who would know that your computers are talking to each other? So anyway, like I said, it was going to be a short day. We just had that one algorithm to cover and then some practical applications for it. So lots to be discovered, lots of open areas for research. If you ever do go on and go for a bachelor's degree, maybe there's some undergraduate research project that you could work on. And certainly if you go and get a graduate degree, an advanced degree, a master's or a PhD, you will be doing research and discovering new things. So even computer science, where you think everything's already been discovered, because what you're doing at this level is you're basically programming stuff that's already been programmed. Everyone's written sorting algorithms. Everyone's written programs to take images and flip and rotate them and blur them, right? So you're basically reinventing the wheel. But at the beginning levels, you have to do that before you can move on to the more advanced stuff that no one's thought of before. So that's basically it. There's no, like I said, no assignment for this week. Anything else to bring up? No? So next week, on Monday, we're going to be going into finite state machines, which is a different kind of graph. It's still a graph, but I think finite state machines are a huge fun because basically from now on for the rest of the semester, we're just drawing pictures. So we're doing math, but we're drawing pictures. Finite state machines are a great way to do things like pattern matching. It's a good way to organize computer programs as the program kind of flows through different phases of the program. And it also speaks to how compilers work. How do compilers recognize those different parts of the program? How does it know that XYZ is a variable name, and how does it know that 1, 2, 3, 4 is an integer? Well, it has to do pattern matching on that to figure out what each of those pieces of the program are so they can tag them appropriately with their token types. So we'll talk about finite state machines, regular expressions. If you've heard about regular expressions before in another course, we'll dig into those a little bit deeper. And then we will show how a computer is able to take a regular expression, which is basically a fancy way of saying a pattern, and turn that into a state machine that then an engine, a computer program, can execute. So it's kind of like taking a regular expression and compiling it into a graph and then executing the graph. So very neat stuff. And that should take maybe 2 weeks or so, 2 or 3 weeks, and then there will probably be some time towards the end of the semester to do some extra stuff. So that's it for today. Short day, like I said. If there's no other questions, then that's it. For those of you in the United States, enjoy your Veterans Day holiday. For those of you in my Tuesday, Thursday class, I have yet to decide whether I might actually hold a session tomorrow or not. You know, we're all online, so it's like, what do holidays matter? We're all going to be home anyway. So I'll be sending out an announcement about that. So that's it. Yeah?
Real quick, I just wanted to kind of you to go over how does the grading work in this class?
Oh, so I'm marking the assignments as being complete or incomplete. And I'm a little behind on that, so I might use my holiday day to catch up on that a little bit. And then towards the end of the semester, you'll have a really quick meeting with me, and we will go over basically your portfolio of work and then see what grades you would get in the class. So I'm basically going to ask you, what grade do you think you should get?
Okay. What do you mean by portfolio? Is it just all the
assignments? Yeah, we'll look at all the assignments and see whether you've completed the majority of them and whether you've improved your work over the semester, and that'll be the grade you get.
Awesome.
So it's kind of like a performance review, right? If you've ever had a performance review with a manager, right? They basically say, "How do you think you're doing?" Okay, so if you're behind on some of the assignments, take the time during the upcoming holiday breaks to catch up. Okay, that's it for today.
All right. Thank you, Professor.
Yep.
You too. Take care.
Have a good
Have a
holiday.
good day.
Bye-bye.
Thank you. Bye, everybody.
All right, and we have, 6 people watching on YouTube. So again, that's it for today. And hope to see you next week. We do finite state machines, fun stuff. Hope to talk to you later. All right, bye-bye.